Hello dear learners, welcome back to this new session. Today we are going to discuss something interesting in the structural mechanics, and our today's topic is the displacement method. Let us move ahead and understand what are the various methods of analysis of the structure. We know that earlier we have already studied the compatibility method, in which the basic importance was given to the degree of static indeterminacy, and this degree of static indeterminacy was been found by the total number of unknown present in the system minus three conditions of equilibrium, and that value is going to give you the degree of static indeterminacy. That means whatever degree of static indeterminacy we shall be having, those many number of unknowns are not able to be solved by the generalized method. There we need certain specific method, and that particular specific method was been derived by generating the compatibility equations at a particular joint. So here in this compatibility method, force was the major source of information. So force was a prime constraint into this particular compatibility method, and once we had the compatibility equation, solving those many number of compatibility equation into that specific problem, we used to find out the unknowns present in the system which were unable to be found out by the conditions of equilibrium. Moving ahead, another method is called as the equilibrium method. This method is also called as a displacement method. Now as far as this displacement method is concerned, which has been also called as the equilibrium method, here as in case of a compatibility method, force was the major constraint or the major focus. Here in this equilibrium method, displacement of a particular joint are going to be the major focus. Is it okay? So in compatibility method, force, it was force oriented, whereas equilibrium method it is displacement oriented, and both these compatibility equations and the equilibrium equations in both the methods are to be observed at a particular joint under consideration. So this is a very important point to be understand at this particular moment. So in both the cases, in first case it is force oriented, that's why we used to find out the number of unknowns in terms of the forces in the compatibility method, and we used to apply the compatibility equations. Whereas in this particular equilibrium method, displacements are going to be the unknowns. Those displacements are to be found out by observing the equilibrium of that particular joint. So this is what is the basic understanding of this compatibility method and the equilibrium method. Moving ahead, today as we have already discussed about the force method, in this the number of unknowns are going to be the major constraint which are to be found out by the formation of compatibility equations, and those unknowns are nothing but those are the forces which are called as the redundant forces, which are going to form the equations, and after solving those equations we are going to find out the redundant reaction. In this particular compatibility method, we have already studied certain methods. So first method is the method of consistent deformation, which is also called as a flexibility method or the unit load method, which we have already studied in module number 3. In this second article was related to the Castiglione's second theorem, which, and these Castiglione's theorems we have already studied in module number 2 and module number 3. Whereas in module 4 we have already studied the Clapeyron's theorem of three moments. So all these understanding we have already got what are this particular method and for what purpose they are been used. And as far as the purpose is concerned, purpose is very simple: to analyze the statically indeterminate structures. Further, there are few more methods which are not at this particular this level it is important. So Maxwell-Moore theorem, column analogy and elastic center method are not at this moment discussed further. So here as far as the equilibrium method, as I have told you earlier, in this equilibrium method displacement of the joints are major focus and which are to be found out, and as far as this unknown equations are concerned, those will be in terms of the displacements of the joint, and after finding out or after identifying the number of displacement at a particular joint, we are going to apply the various conditions. So what are these? So first of all, displacement equations are being found out in terms of the external load which are happening at the particular joint. Now after finding out this particular thing, we are going to find out the redundant. In this, the redundants are nothing but these are the displacements. So here one thing is very much clear, that prime constraint is the displacements occurring at a particular joint. Secondly, we have to find out the relationship between the displacements and the applied load, and then we have to apply the equilibrium condition at a particular joint, and after applying that equilibrium condition, we will be getting certain equations which are to be solved. As far as this methodology is concerned, we are going to study the slope deflection method which occurred in the module number 5, whereas the next is a moment distribution method which is a part of module number 4. So beyond these two methods, there is one more method, that is minimum potential energy method, that we are going to see afterwards. So right now we have been focused on the slope deflection method which was been developed by Axel Bendixen from Germany. Now what he has done and what are the methodologies which are to be adopted for the analysis of this structure by the slope deflection, that we will see one by one. So let us see what are the today's contents. So here we are going to understand the usefulness and uniqueness of this slope deflection method. Next to that, we are going to understand what is this kinematic degree of indeterminacy. Next, sign conventions. Then we are going to see the basic concept what is to be applied into this particular sort of a problem, and then at last we are going to understand the derivation of slope deflection method, that is the governing equation of slope deflection method. So these are the various contents which we are going to see one by one. So moving ahead, let us see what are the uniqueness and the usefulness of this particular slope deflection method. So as far as the usefulness is concerned, here we are going to understand the relationship that is going to exist between the displacements of the joint and the forces applied on that particular members. So displacements are going to occur due to the applied forces on the members. So we have to establish the relationship between these two, that is the displacements and the forces applied on that particular members. Uniqueness. As far as the uniqueness is concerned, as I have told you, in force method, in earlier compatibility method, force was a major constraint, and here the displacement of the joints are taken into consideration. Now not only understanding the displacements, and as far as one more thing is to be made very much clear, when I talk about a displacement, there will be always three types of displacement. One in horizontal direction, second in vertical direction. Both horizontal and vertical will be linear. As far as the third type of displacement is concerned, it will always occur into clockwise or anti-clockwise sense. So these three displacements will be the redundants into this particular displacement method. All of you are getting? So this is what is the thing or the uniqueness of this. Beyond that, what is the further uniqueness? After having this understanding of the displacement about a particular joint, in that member we are going to have the set of algebraic equation in terms of the displacements. Now once we find out this set of algebraic equation, we know what is to be done. We have to solve it simultaneously, and we have to find out the redundant unknown into this particular sort of the problem. Further moving ahead, after finding out the set of algebraic equations, finding out the displacement, then the final steps comes to find out the final moment. So this is what is the uniqueness of this. So in three steps only, we are able to understand the behavior of this total beam or that particular structure. So this was the usefulness and the uniqueness of this particular thing. Now the most important thing when it comes to a displacement method is to understand this degree of kinematic indeterminacy. As we have already studied what is the degree of static indeterminacy, Similarly, we are going to study what is the kinematic indeterminacy. To be very specific, let us understand two words. One is static and another is kinematic. We know static is the body under stationary condition, whereas kinematics is the branch of dynamics. So dynamics is always related to the displacements. So that is why this kinematic word is occurring into the displacement method, not in the earlier method, that is a compatibility method. So basically the two words static and kinematic are just because of the theory which is occurring behind the methodologies or the philosophies behind that particular methodologies. So here, as we are dealing with the displacements, in order to have a displacement there has to be certain motion. So about a particular joint, whatever motion is going to take place, horizontal, vertical, or the clockwise or anti-clockwise, those are nothing but those will be the displacements occurring at that particular joint. So this particular terminology, that is degree of kinematic indeterminacy, is very important to understand before understanding the displacement method or any methodology related to this displacement method. So let us understand what is this degree of kinematic indeterminacy. Now here, understanding the displacement of that particular structure is a prime important. So in order to understand that particular displacement, and those particular displacements are also called as what? Kinematic unknowns, or the kinematic indeterminacies, or the kinematic redundants. So let us understand how this kinematic redundants are to be found out. So let us take one example. We can see in this figure number 1, it's simply supported beam with certain sort of a loading. So here at A and at B we can observe two types of simple supports. One is hinge, another is also hinge, and we know the peculiarity of this hinge, it always allows the rotation about its own point. So here hinge is provided here, so this hinge is allowing the rotation of this beam in this clockwise direction about point A. So that displacement is the slope of this. So here you can see the displacement at joint A due to the presence of hinge is equal to theta A. Similarly, it happens about point B. Being hinge, it allows a rotation of magnitude theta B. So in this first example, there are two rotations occurring, and these two rotations are theta A and theta B. As two rotations means two displacements at A and B, that's why the degree of kinematic indeterminacy comes out to be equal to 2. Let us understand further. This is another example in which one end is fixed and other end is the hinge. Is it okay? So we know the fixity effect. It is never going to allow the rotation. It has certain resistance against rotation. So A is not going to rotate, whereas B is going to rotate. So there is only one rotation. That's why what we have, dki is equal to 1, as only one displacement is occurring into this particular sort of a problem. Is it okay? In the third case, one is A support is fixed support, so no rotation. At B there will be a rotation, but here this rotation occurring about point B is not been held by joint C, as there is no any support. So this joint C will directly move downward. So in this specific problem, there are two displacements. One displacement is rotation and another displacement is the vertical displacement about point C. So here there are two displacements, theta B and delta C. So the dki is equal to 2. So this is what is very important aspect to understand, what are the displacement occurring in that given problem, and after understanding the displacement in that problem we will be able to understand what is degree of kinematic indeterminacy. So after finding out the kinematic indeterminacy, we get an idea how many unknown redundants are going to be there. So we can see here in this there are two unknowns, theta A and theta B. Here theta B is the only unknown, and here theta B and delta C are the two unknowns which are to be found out by the method of slope deflection. So let us move ahead and understand the various sign conventions which will be following throughout while understanding this particular slope deflection method, and I know that these are usually the universal sign convention. So let us talk about the first, that is a moment. So we know we are going to have certain reactions and certain loadings for which we have to take the moments. So here, whenever there will be a clockwise moment of that particular force, it will be taken as positive, and otherwise it is going to be taken as negative. So clockwise moments are positive and anti-clockwise are negative. As far as the displacements are concerned or the vertical forces are concerned, upward force are always taken as positive and downward forces are always taken as negative. Moving ahead, as far as the rotations are concerned, so here you can see if a joint is rotating in this particular way, so here you can see the rotations of a joint. So here there is a fixity, so it is giving a resistance toward the rotation. As far as this B point is concerned, it is hinge, so it is allowing the rotation. So this beam is going to rotate in this particular fashion. It is going to rotate in this elastic curve manner. So here anti-clockwise couple is responsible for pushing this part of a beam in the downward direction, and for this right hand part of this particular beam, this anti-clockwise same couple is pushing the beam in the upward direction. So that's why this single couple about this joint is going to rotate in anti-clockwise direction, which is causing the rotation, and because of that there will be the rotation happening for this left part of a beam and the right part of the beam. So whenever there will be a clockwise rotation, it is to be taken as positive, and if it is anti-clockwise rotation, it is to be taken as negative. So this is what we have as a sign conventions. Now what basic concept we are going to apply for this, that is very important to understand at this point. So first of all, whenever whatever beam will be given with any sort of the support system, first of all we are going to consider the spans individually, and we are going to find out the fixed moment for that individual span. Is it okay? So as far as the knowledge of fixed moments or fixicity of the beams are concerned, that already we have gained into the earlier lectures. Please go through the earlier lecture so that you can understand what I am talking about, the moments at the end. So whatever type of a beam is given, with whatever type of a support, with whatever type of a loading, first job is to find out the end moments. And secondly, as we know, at every joint certain displacement is going to take place. Due to those displacements, certain moments will be induced into that, and those will be in terms of couples about that particular joint. So those rotations or those displacements are going to introduce certain moments about that particular joint. So there will be two moments occurring. First moment due to the external loading, second moment due to the internal displacement about that particular joint. So once we get these two, we are going to have a arithmetic operation onto these two what we can say moments. One moment is moment at the end due to the fixicity, and second is the end moments caused due to the displacement about that particular joint. So after having mathematical treatment to these two moments, we will be getting the set of equations, and obviously they will be the simultaneous equations in terms of the displacements. After solving those simultaneous equations, obviously we are going to get the redundant displacement, and after getting those redundant displacement, we are going to consider the equilibrium of particular joint, and then after substituting the equilibrium condition or the various values into that equilibrium condition, we will be ultimately getting the final moment occurring into that. So here you can see, as I have told you, displacement will be there and the final end moments will be there, which are to be found out by the slope deflection methods or the governing equation of slope deflection. So this is what is the philosophy behind this particular slope deflection method. Now when it comes to a continuous beam, how it is to be applied, so it's very simple. Consider the spans individually. So consider AB span first, do all this, then proceed with the BC span, observe all these various mathematical part, and then consider at last the last part, and then observe the same again procedure. So this is how we are going to get the final solution by this particular slope deflection method. So in continuous beam, always remember we have to detach the spans and consider the spans individually and apply the governing equation of slope deflection. So this is what we have as a basic concept. I hope you all are getting what is this slope deflection method. Now moving ahead, let us understand the backbone of this. What is the derivation or the governing equation of this slope deflection method? So in order to understand that, let us take this first example. This is the fixed beam. At A and B there is a fixed support, and W1 and W2 are the loading applied, and the span is equal to L. Is it okay? So I know what is the friction moment. MAB bar is the friction moment at A, and MBA bar is the friction moment at B. So we know how to find out this friction moment by the knowledge of friction beam. We know what are the friction moment of this particular cases. Is it okay? So after finding out that, as I have told you, due to the applied load on the beam, there will be the friction moments, and these friction moments are not going to give you the complete solution. But as we are dealing with the displacement method, due to this applied load there will be displacement at A and B, which will introduce the moments about A and B, and after compiling the friction moment and the moments induced due to the displacements occurring at individual joint, we are going to get the set of what we can say equations, and after solving those equations we will be able to find out the final solution. So this is what is the first case. Here we are having one fixed beam AB with loadings and the friction moment. Now what exactly is to be done, let us understand. Now in order to find out the final moment about point A and B, this is not B and C, this is A and B, these moments about A and B will be finally treated when we take into account every moments happening into this particular sort of a problem. Let us see what are the various moments happening into this. As far as this A point is concerned, we know the final moment about point A will be what? The moment due to the fixicity effect, that is already taken into account in this first figure, MAB bar, plus moments caused due to the displacement at A and B. And what are the displacements occurring? That there may be rotation about point A, there may be rotation about point B, there may be translation about point A and B. Is it okay? So this is how we have to combine all the moments due to the various effects. So first effect is the fixicity effect, and second effect is due to the displacement occurring. So I have combined both the effects in this so that we can find out the final moment MAB about point A. Similarly for this BA, B to A. So what is that? It is the friction moment plus moment caused due to theta A, theta B and delta B. That is the rotation and the displacement about point B. So this is how we are going to combine all the moments occurred due to the applied forces and the displacement occurring about that particular joint. So we get the final moment. Now let us understand what are this moment caused due to the displacement. So first of all we are going to consider the displacements one by one. So first displacement, let us take the rotation about point A. So when it is going to rotate? When it will be a hinge support. Right now there was a, in the initial problem there was a fixicity, but I have to assume that there will be rotation due to the assumed support at point A. So I have considered here a hinge and I am allowing this joint A to rotate in this particular fashion. So here you can see it is rotating in a clockwise sense. Is it okay? So after understanding this, you can see certain moments are being going to get introduced. This 4EI by L into theta A is the moment magnitude induced due to the rotation about point A of magnitude theta A. Is it okay? So this particular standard case already has been seen into the earlier articles. So here the moment near the point under consideration, that is point under consideration is A. So the moment caused due to this displacement is called as a near end moment, and moment caused due to the rotation about point A has been distributed on the far end, and that is called as a far end moment. So you can see here near end moment is 4ei by L theta A, whereas half of the moment will be transferred at the far end. So that is equal to 2ei by L into theta A. So this is what is the understanding of the first moment caused due to the rotation about point A. So here why it is happening, all this particular effect, due to the fixicity has been released and assumed support is taken into account, and the assumed support is a hinge support which is allowing the rotation about point A. Hope you all are getting what is happening into this particular thing. So this is what is the effect due to the release of fixicity about point A and assumed hinge about point A. Is it okay? So due to that there will be effect at the near end as well as there will be effect at the far end. Now let us take the another displacement, that is theta B. So theta B is the rotation happening about point B. So here you can see the rotation happening about point B. Is it okay? So again there will be a clockwise couple which is trying to push this beam in this particular direction, and this clockwise is going to rotate that particular joint B by the magnitude theta B. Is it okay? So why it is happening? Because the fixicity at point B has been released. It is assumed that it is been released and substituted by the hinge, because unless hinge is there it is not going to allow the rotation. Is it okay? So due to the hinge assumed support here, it is allowing the rotation about point B, and because of this rotation displacement in the clockwise sense, there will be a moment introduced into the joint under consideration. So thus that moment value or magnitude is equal to 4ei by 4ei L into theta B. Is it okay? So this is near end moment now. What is the point under consideration? B. So its near end moment is 4ei by L into theta B. So as what happened in earlier case, half will be transferred to the far end. So 2ei by L into theta B, which is called as a far end moment. Is it okay? So this is due to the rotation occurring at about point B. Now let us take the final displacement happening into this. So for example, I am going to consider that there will be a sinking effect about point B. So because of which there will be the magnitude delta B of the sinking effect. Is it okay? Or we can say these two supports are at a different level of level difference of delta B. Is it okay? Because of this, certain moment will be introduced about joint A and about joint B. Is it okay? So you can see this moment is trying to push this joint B in the downward direction, and that is a anti-clockwise sense moment happening, and its magnitude is equal to 6ei by L square into delta B. Is it okay? So this is what is the magnitude of a moment happened due to the couple induced due to the deflection of joint B in the downward direction. Is it okay? So this 6ei by L square delta B is the moment induced due to the vertical deflection of point B. Similarly, this is a near end effect, far end effect is also there. So here we know that whenever couple is acting, wherever it acts along the beam length, it is going to be same. So that is why, as this is minus 6ei delta by L square, so this is also minus. Why minus? Because both are anti-clockwise. So couple, it acts anywhere, it is going to have the same effect. So this is what is the anti-clockwise couple of magnitude 6ei by L square delta B acting at B, same is been transferred at point A. But the effects of this are different. Here it is trying to push it downward, here it is trying to push it upward. So this is what is the understanding of the displacements and the moment induced due to the displacement. Now let us understand further what will be the final end moment about point A. So here in this case, first will be what? Plus or minus MAB. Why I am taking plus or minus? Because Here in this case, fortunately, it is anti-clockwise. It can be clockwise also. So right now there is no any specific problem as such, so we don't know what exactly it will be, but definitely once we know the sign conventions, accordingly we are going to put the value of plus or minus here. So here MAB, plus or minus MAB. So this is first friction moment due to the applied forces on the beam. Is it okay? Now let us understand the moment caused due to the displacement about various points. So next to that is this. So I am considering joint A and the moments happening about joint A due to the various displacements. So here final moment will be fixicity effect, then rotation about point A. So again it will be plus or minus because it can be clockwise or anti-clockwise. Accordingly we are going to select plus or minus. So first and second. Third will be what? 2EI by L. That is the effect of displacement occurring about joint B, and that displacement is the rotation of magnitude theta b. Is it okay? So I am just adding all this one by one. So first MAB bar 4EI by L theta A, then 2EI by L theta B, and the last one is obviously plus or minus 6EI by L square into delta B. Again plus or minus when clockwise it is plus, anti-clockwise minus. Is it okay? So this is how we have found out the final end moment about point A by considering the friction moment as well as the displacements occurring and displacement effect occurring about each and every joint about point this particular A. Is it okay? Similarly MBA is to be worked out. So here you can see MBA bar plus 2EI by L theta A plus 4EI plus here I am taking plus or minus, accordingly here I am having plus, so 4EI by L theta B, and here at last it will be plus or minus 6EI delta by L square. Is it okay? Once again I have to make it very much clear. I have given the universal sign. If it is clockwise, take it positive. If it is anti-clockwise, take it negative. So I am trying to find out a generalized governing equation for the slope deflection. That's why I am put it plus or minus. So if I have to apply this particular governing equation for this specific case, let us see how it works. So MAB will be equal to anti-clockwise, so minus, this is plus, so plus 4EI by L into theta A plus 2EI by L theta B minus 6EI by L square theta B. So this is how we have worked out equation number 1. So what I did here, I can take EI by L outside as a common. So in bracket we have 2 theta A plus theta B minus this particular remaining terms. So this is a governing equation for finding out final end moment about point A. Similarly I can work out for the final moment about point B. So on the same lines I have added all these according to the sign convention. So here it is plus, so plus, so this is plus 2EI by L plus 4EI by L and minus 6EI by L square theta B. Is it okay? So this is how I have to work out the governing equations for this specific first beam which is fixed at A and B. So as I have mentioned you earlier that whenever we are going to come across a fixed beam, this is a analogy to be applied for that particular analysis of the problem. But when it comes to a continuous beam, that also I have already mentioned, consider the spans individually. Take first span, then take the another adjacent, and then the third one. So and for every individual span under consideration we have to apply this governing equation, and we are going to work out the set of equations. So as I have told you earlier again and again, so this is what is the first equation A, which has two unknowns theta A and theta B. Second equation I have again in terms of theta B and theta A. So there is only this particular sort of a single span beam, so there will be only two unknowns theta A and theta B. So after solving these two simultaneous equations A and B, these are forming the set of equations, two equations. Solve them, you will be getting the value of theta A and theta B. So this is how we have to understand the slope deflection method governing equation. Is it okay? So always remember this equation for an individual span, and always remember the sign conventions to be adopted for that individual span. So this is what we can understand for this slope deflection method, and this is how we have to work out the various final end moment. So I hope you all are getting. Now moving ahead, moving toward a very last part and the most important part of this particular uh, understanding of the analysis of the structure. This is what we have already studied earlier. We are just going to revise at this moment. So let us see what are the various boundary conditions. As I have told you, we have to apply the, or we have to understand the joint. So there will be certain boundary conditions. So here in this particular case, we can see a fixed beam, and obviously it is a continuous beam ABC, which is fixed at A and C. So here you can see at joint A and at joint C, fixed supports are there. So no any rotation is going to take place about point joint A and joint C. So no rotation, so no slope. So that's why we say slope at A and slope at C is equal to 0 due to the fixed and support. Is it okay? So the supports are fixed, so no rotation, so no displacement in terms of rotation about this particular joint A and C. That's why that is equal to 0. Is it okay? Now in second figure you can see joint A is what? Joint A is hinge, whereas joint D is fixed. So in this second figure you can see at joint D being fixed, slope at D should be equal to 0. So slope at D means what? Theta D is equal to 0. Theta D is equal to 0. Is it okay? So this is what is the second of understanding of the rotation as a displacement. Now second, let us understand rotation displacement in terms of the level difference or the sinking of the effect. So here in this case, if joint A is not going to sink downward, that means delta for span AB or span BA, this is span BA, should be equal to 0. That's why in that governing equation this term will be equal to 0. So theta delta EI delta 6EI delta AB by L square will be equal to 0. Similarly for the another end moment also it will be equal to 0. Similarly, if joint C doesn't have any sinking effect or level difference of this particular support, so what we can say, delta for CB is equal to 0 and delta for CD should be equal to 0. That is why in governing equation these two terms will be equal to 0. So this is what is understanding the boundary condition about the displacement in terms of rotation and the sinking of that individual joint. So I hope you are getting what I am talking about, this particular boundary conditions. So this boundary conditions are been already used so many times earlier. We are just revising all this. So first of all we have talked about the boundary condition. Moving ahead, let us see what are the equilibrium condition of a joint. As I have told you earlier also, in compatibility method we used to consider the joint where we used to find out the compatibility equation. Similarly on the same lines here also we are going to consider a joint, but here we are going to understand the equilibrium condition of that particular joint. Is it okay? So let us see what is that equilibrium condition for a particular joint. So here for example, let us take an example of this continuous beam DABC. Here this is a continuous beam supported at A, B and C, whereas this D part is D point is overhanging with certain type of a load. Let us take this particular universal example, what happened into this particular and what are the equilibrium conditions. So here in this case, as we know, this joint A, how it is to be brought under equilibrium. If I draw the separate span for DA and AB, so here you can see MAD and MAB. Is it okay? At this joint A, equilibrium has to exist. Means what? The total moment or total couple moment about point A should be equal to 0. That is why we have MAD plus MAB is equal to 0. So you can take it the universal. This is plus, so this is minus is equal to 0. Is it okay? So total resultant couple at this point has to be equal to 0. Is it okay? Because this is a hinge support. All of you are getting? So in order to work out this value of AD, what I did, I have considered overhanging part only, AD. For example, there is a 50 load acting at a distance of 3 meter. So we know if I take a moment about point A, this will be what? 50 into perpendicular distance 3. 150 will be the magnitude. But in which sense? It is happening anti-clockwise. So minus 150 kilonewton meter will be the moment about point A. Due to that moment, as this is the action happening due to the applied load, there has to be the reaction. So reaction at this point will be MAD. This is resisting the overturning of this overhanging part of this particular beam. Is it okay? So action is anti-clockwise, so reaction has to be clockwise. So that's why I have taken it here. MAD should be equal to plus 150 kilonewton meter. Is it okay? Once you find out this particular MAD, as far as this MAB is concerned, that we can find out by considering an individual span of AB. Is it okay? So once I have MAB and MAD, so equilibrium of joint A is that MAD plus MAB should be equal to 0. Why? Because the total resultant moment about this point has to be equal to 0, because we know about a simple support there will not be any moment occurring, or the at simple support moment has to be equal to 0. Is it okay? So this is how the first what we can say equilibrium condition we have tried to understand by this particular example. Moving ahead, let us understand what is to be done with the remaining joints, as I have taken here only the joint about which there was a overhang DA. Is it okay? So joint A we have taken. Now what happens about this joint B? Is it okay? So here, so this MAD plus MAB is equal to 0, that already we have seen, and the second equilibrium condition about joint B will be MBA plus MBC should be equal to 0. Is it okay? So resultant couple about this particular joint B has to be equal to 0. So after substituting this value of this MBA plus MBC is equal to 0, you will be getting the set of what we can say simultaneous equation, and that we can solve it for the unknown or the redundant displacement. So this is what is the equilibrium condition happening into this particular type of a beam. So moving ahead, in the next class we shall be looking after for the slope deflection method numericals. So I hope you all are getting what is the slope deflection method and what is the procedure to be followed, and you have also understood, I guess, how that governing equation is to be formed. So this is what we have for today. Have a nice time and thank you very much.